Thanks a lot, Steph. So today I want to present you a TMS study where we show that the left inferior parietal lobe and auditory cortex jointly contribute to the retrieval of sound-related conceptual knowledge. So as a bit of background, so-called grounded cognition theories propose that concepts consist of perceptual and motor features. Yeah? So for example, if you have a concept like dog, it should consist of the typical visual shape of a dog, of course, its colors, its motion patterns, the sounds dogs make, yeah, such as woof, and the actions we as humans perform with dogs, such as petting them, right? And now the key idea of these theories is that these features are represented in modality-specific perceptual-motor brain regions. Yeah? So for example, action features would be represented in somatomotor regions, of course. They're also engaged in real action execution and sound features in auditory brain regions. And we performed a meta-analysis across 212 neuroimaging studies on conceptual processing, which essentially provided support for these theories. So action-related conceptual processing, for example, consistently engaged the brain regions here shown in blue, and these partially overlapped with brain regions involved in real action execution, as you can see in red, and in purple you see the overlap. And sound-related conceptual processing, as another example, consistently engaged the brain regions shown in blue that are also engaged in real auditory perception, such as the bilateral posterior STS, for example. However, we also found evidence for so-called multimodal brain regions that are consistently involved in multiple modalities. So for example, the left inferior parietal lobe, the IPL, is consistently engaged in conceptual processing related to sound, action, and motion. So these kinds of results suggest that conceptual processing involves both modality-specific perceptual-motor regions and multimodal convergence zones. Then, using effective connectivity analysis of fMRI data, we could show that multimodal and modality-specific regions also functionally interact during conceptual processing. So, for example, during the processing of sound-related words, such as propeller, we saw increased coupling between the multimodal IPL and the left auditory cortex. And during the processing of action-related words, such as napkin, we saw increased coupling between multimodal IPL and the somatomotor cortex. However, this is just fMRI data, right? So it remains completely unclear whether these network interactions are actually causally relevant for conceptual processing on a behavioral level. And this is what we wanted to test in this condition and perturb TMS study, where the key research question was, is the functional interaction between multimodal IPL and auditory or somatomotor cortex causally relevant for sound or action knowledge retrieval, respectively? And these are the nice people that were involved in this project. So we invited 24 young and healthy subjects for 3 sessions where we performed offline TMS over modality-specific region, so somatomotor cortex, auditory cortex, or sham as the baseline, which was then followed by online TMS over the multimodal IPL, or again sham as a baseline. And so each session looked like this. We performed 1 Hz RTMS for 15 minutes offline, which was then followed by 4 blocks of sound and action knowledge tasks where online TMS was applied over one of the 2 regions. Then we had a break of 20 minutes, and then we did the same stuff again, so 1 Hz RTMS for 15 minutes, followed by task blocks and online TMS over the other region. So in each task block, we presented written words that had a high or low association with both sounds and actions. So we have 4 categories: high sound, high action words, such as guitar, right? Guitar is something that makes a sound and that you interact with, right? Then high sound, low action words like propeller, low sound, high action words like napkin, and low sound, low action words like satellite. And then during sound judgments, participants had to judge whether the object denoted by the word is strongly associated with sounds or not via button press, yes or no. And during action judgments, they had to judge whether the object is strongly associated with human actions. So do we interact with this object typically? And on each word presentation, we applied 5 pulses of TMS at 10 Hz. Now, for kind of the first time, I believe, in a higher cognitive study, we used a priori computational electric field simulations, where the goal was to optimize both targeting and dosing for each of our stimulation targets. Yeah? So in our pipeline included a state-of-the-art motor mapping protocol as a kind of reference point for electric field-based dosing. So as a kind of first step, we created high-resolution head models based on subject-specific T1, T2, and diffusion-weighted images using SimNIPs. Then we acquired TMS at about 300 positions around the presumptive motor hotspot and recorded the associated coil positions and EMG muscle responses, right? How strongly the finger twitches. Which then gave us a pair of the MEP magnitude as well as the E-field magnitude for each pulse, right? So we performed an E-field simulation for each pulse. And then you can perform a regression between the electric field magnitude and the MEP magnitude in each cortical element, which then allowed us to determine the motor hotspot, which can look like this. Of course, I picked the subject where it looks particularly nice. And then we optimized targeting for the motor hotspot as well as for the auditory, somatomotor cortex, and the IPLs, or cognitive targets, so to say, by searching in a 2 centimeter search grid for the optimal coil position that maximizes the E-field magnitudes in each target. And then finally, we optimized dosing by, for each target, matching the stimulation intensity to the individual E-field strength in M1 at RMT, right? And so in this way, we now kind of equalize the stimulation intensity both within subjects, as you can see, and also across subjects then, right? And this is, I think, much better than, for example, resting motor threshold-based dosing, what everyone did before, we as well, right? Sorry. And here you can see the variance you get if you do this. All right, then for behavioral analysis, we use the so-called drift diffusion model, which analyzes response times and accuracies together, accounting for potential speed accuracy trade-offs and response biases, right? So the drift diffusion model kind of assumes that the subject accumulates evidence from the stimulus starting at a starting point Z, right here, until reaching a decision boundary either at A for yes responses or at 0 for no responses. And the drift rate is the average rate of evidence accumulation and the key parameter of interest as it closely reflects behavioral performance, right? So the steeper this curve is, the better people are, so to say. So after the model was fit to our data, we analyzed the drift rate data further. And here are the results, finally. This is kind of a complicated plot, but I will walk you through it. So what I'm plotting here is the change in drift rate between effective stimulation and sham stimulation, right? So lower than 0 here means people got worse with effective TMS. And what we found was that combined auditory plus IPL stimulation in yellow selectively impaired sound judgments on low sound, low action words. This effect was anatomically specific, as it was significantly stronger than for IPL-only stimulation in blue, auditory-only stimulation in orange, somatomotor-only stimulation in purple, and somatomotor plus IPL stimulation in green. And we also found evidence for task specificity, as the impairment of sound judgments by auditory plus IPL stimulation was significantly stronger than for action judgments on the same words. Yeah? So I think we can conclude that combined auditory plus IPL TMS selectively impairs sound judgments. Then to kind of characterize the relationship between these behavioral effects and effective stimulation of each target, we performed a Bayesian regression between the E-field strength in each target and the behavioral effects. And we found that the behavioral impairment of sound judgments was best explained by the electric field in the auditory cortex. Yeah? So as we can see here, there's kind of a negative correlation between the E-field strength in the left auditory cortex and the sham normalized drift rate for sound judgments. So in a normal language, people who were stimulated more strongly in the auditory cortex got worse at sound judgments, right? And so I think this really strongly suggests that the sound judgment impairment is indeed driven by auditory cortex stimulation. So I think we can conclude that the joint contribution of the multimodal IPL and the auditory cortex is indeed causally relevant for sound knowledge retrieval. The functional relevance of the left IPL seems to depend on the integrity of the auditory cortex and vice versa, as single perturbation of either region did not disrupt performance. And this supports so-called hybrid theories of conceptual processing, which propose that both modality-specific and multimodal brain regions are crucial, such as our model that I, of course, want to advertise here, which we proposed last year, which assumes that the conceptual system relies on a neural hierarchy from modality-specific regions to multiple levels of multimodal convergence zones, including the left IPL. And with that, I want to thank my group, the research group Cognition and Plasticity at the Max Planck Institute in Leipzig, and I want to thank you for listening.
Thank you. One very quick question for you. How do you biologically interpret a great negative coupling between two regions?
A negative coupling between two regions. I think in terms of DCM, this typically reflects inhibition, right? So I think I don't know if I can go back to the slide, but anyways, so we saw a negative modulation by action words on the interaction between the motor cortex, somatomotor cortex, and the IPL, which I think could reflect that the motor cortex inhibits the multimodal IPL during action knowledge retrieval, which then again, what this means, I'm not exactly sure, but for example, one idea could be that the somatomotor cortex becomes more relevant during action knowledge retrieval, right, and then decreases kind of the influence of this multimodal area.
Thank you. We're moving